This video is from my earlier course, back when I was building out these ideas. The fundamentals I cover here are still solid, but the frameworks have evolved significantly since then. Head to systemthinkinglab.ai to see how this turned into a full course series. Hello, and welcome to our next lesson, tasks, zeros and ones that transform data. Let's get started. So the goal of this lesson is to understand how tasks, or instructions, manipulate and transform raw data into meaningful outputs. We'll explore how binary instructions, zeros and ones still, guide computers to perform computations, turning static data into something useful. So, what is a task? A task is a defined unit of work that the computer performs. It takes certain inputs and produces outputs by following a set of instructions. In essence, a task encapsulates a small piece of logic or computation. And this idea of a task is the fundamental area of computing, of programming, I would say. The idea that you can take a problem and break it down into a series of tasks that are executed when certain conditions are met sequentially, delayed, doesn't matter. But the idea is that you can take a problem, break it down to a bunch of tasks that have inputs and outputs that are executed. This is the fundamental paradigms of computing and the fundamental paradigm of programming. And so that's what we're defining here as a task. Tasks are zeros and ones. At the lowest level, tasks to the CPU, or central processing unit, are represented as binary digits, just as storage. This is a key insight. Storage, which is data that's stored and organized in a certain way using data structures, and tasks as well, are both zeros and ones. They are both represented by transistors physically in the CPU or in the RAM or in disk storage or what have you. This is a key insight. Zeros and ones, storage and tasks. So just like storage, the instructions themselves are stored in memory as sequences of bits. Bits mean zeros and ones. These bits tell the CPU what operation to perform next. So distinguishing storage from tasks. So again, both storage and tasks are stored as binary, but how we interpret them differs. So storage, we interpret the same zeros and ones as information, like numbers, text, images, so on and so forth. Tasks, you take those same zeros and ones, but they represent actions to be performed on the data, like add two numbers or add more values in memory. This is the key difference between storage and tasks, even though that they might be represented in binary, represented by zeros and ones, but how they're interpreted, how they're used are different. And that makes the key difference between storage and tasks. So again, this is the essence of programming. Programming is about writing instructions that the CPU will execute. From punch cards to assembly language to the high level programming languages that we have today, they all do one thing. They are different ways in which we submit instructions to the computer for the CPU to execute. High-level languages like Python, Java, C++ provide human-readable syntax, or at least a lot more human-readable than zeros and ones. These programs are eventually translated into binary machine instructions the CPU can understand, because once again, the CPU understands zeros and ones. So, functions as tasks. So in many programming languages, a function represents a well-defined task. They have very specific characteristics. A function takes input parameters, one or many parameters, or sometimes none, processes them, runs a number of instructions based on those input parameters, and then once it's done, returns a result. So really clear, a function usually has a well-defined purpose. It takes defined input parameters. It has instructions inside of it and returns a result. This may sound basic, and especially you engineers, you've been most likely been programming off and on either on your own or in classes or in boot camps, and you understand what a function is. But you see, we're moving functions as tasks, functions in the context of system design. This idea of writing things in functions and the idea of having building blocks that build complex systems are not dissimilar. These are one of the same. It's the same logic. We are trying to encapsulate modules that connect with each other that we fully understand in order to create complex systems. So that's why here we're really going into the fundamentals of like, we had storage in the previous lesson. Now we're talking about tasks. If you can think of a function, then you can think of higher level, even higher level functions that would be part of system designs as building blocks. But we'll talk about that in the next lesson. But right now, we're thinking functions, zeros and ones as tasks. Internally, the function's logic is compiled or interpreted into instructions, which again are zeros and ones. So a task or function often looks like the following, like its function, input, returns, and output. You see this in math all the time, y equals f of x. The idea is, especially, let me just write that down. If just ever seen something like this, right, is that you have x as an input, you apply a function to it, it returns y. Similar concept. The input data flows into the task instructions transforms it, and the output emerges. This transformation is the core of what makes raw data meaningful. And let's go into what that means. So how tasks execute. So tasks are called or invoked by other parts of the program. And then when you get into system design, other systems as well, other modules, other building blocks, but we'll talk about that in later lessons. When you call a function, the CPU fetches the function's instructions from its memory. It then executes these functions step by step, manipulating data accordingly to what the instructions state to do. All right? So the CPU's role is the hardware that understands and runs these binary instructions. It carries out fundamental operations, arithmetic, logic, data movement, control flow, and each executing instruction brings the system closer to completing the intended task. Okay, so let's give an example. So let's consider a simple task, add two numbers. The input is two numbers, data. Instructions, perform addition. Output, a single integer or number, new data. Behind the scenes, binary instructions guide the CPU through each step. Now, let's just say, I'm a Python person, right? So you define a function or a task, I'd say, as this. So here you go, say, hold on one second. Hold on. So you want to say define. Say add. Okay? So you define the add, and then you want it to have two inputs, two parameters, right? So let's give it an X and a Y. Okay? Right? So I will first say, okay, the instructions now, perform addition. With this higher level language, we don't have to write 16 different, assembly language lines here. We can write a few lines here. So I'll have another line here. I'll say result equals X plus Y. It takes the X and the Y, it adds them, puts it in result. And then now, but this is not enough. I want to make sure it returns so that the output is what we want it to be, the addition of two numbers. So you say return result. And then basically, so now, if you, let's say in a different function, in different part of the program, if you want to use it, you would just say, okay, let's just say y, or just find something, equals, add, now pivot two numbers. And then so we'll find that y is equal to 7. Because I put 3 and 4 to add, it executes it, passes 3 to x, 4 to y. It's added to the result, it's returned to the result, the result of 7 is put into y, and now we know that y equals 7. Why am I doing this? The idea, though, here is that all of these instructions, define, add, results, so on and so forth, are ultimately zeros and ones that are executed by the CPU in order to do this operation. Understanding that we're encapsulating here and add the ability to add. The instructions are encapsulated there. This is what we're going to do with building blocks. Another layer that you have different building blocks that you use in your system designs that will have inputs, that will give outputs, that will have trade-offs, that will have advantages. That you'll know when to use them, when not to use them. But if you understand these building blocks, then you're able to connect and understand larger and more complex systems. All right? So, what is the relationship with this in data structures? So tasks do not work in isolation. They interact with storage, which are zeros and ones organized in one or more data structures. Tasks process storage for a particular purpose, just like storage can be as simple as storing a number, storing an integer. In the add example, we passed in two numbers as storage and then outputted one number as a result, the addition of the two numbers. That's like shows the relationship between storage and tasks. But combined, as you add more functionality, so on and so forth, they can form building blocks of systems. Storage, what we have, plus task, what we do with it. So this is how we can get complex tasks. That gets into more complex building blocks. Complex functionality is built on combining smaller tasks. Example, processing a file, then filtering a file, sorting it, and summarizing results involves multiple tasks. Each task is another set of binary instructions orchestrated to achieve the larger goal. And the idea is that you can use tasks, the ability to have some sort of area that has input, does some processing, has an output. If you have it defined as a function or what have you, you can use it in different areas or combine it with other functionality to build the fundamental pieces of system design that you can fully understand, yet is easy to understand, but yet also easy to maintain and easy to extend as well because of how modular you made it. So, real world analogy. So think of recipe, tasks, and ingredients as storage. The recipe or task tells you how to combine and transform the ingredients, which is the storage. And the end result output is a prepared dish, which is meaningful data. Okay? So well-defined tasks improve maintainability and scalability. When you have clear task boundaries or modularity, right, it will help you understand and reason about the code of a complex system. This leads to designing building blocks that are easy to extend, debug, and optimize, as I mentioned earlier. So, next steps. So the idea here is that tasks are instructions represented by zeros and ones, just like storage are. And it tells computers what action to perform on the data. Understanding tasks helps you see how raw data is transformed into meaningful output. You have the inputs, it has a set of instructions, outcomes and output. So next, understanding first the storage of zeros and ones in different data structures, and understanding tasks as a series of steps and instructions that transforms inputs into meaningful data outputs. We will then explore how multiple tasks and data structures, multiple tasks and storage fit together into building blocks that are used in larger system designs. Thank you so much, and we'll see you then. This was from my original course on system design for junior engineers. Since then, I've refined and expanded everything you just saw into the full system thinking and AI era course, using these same building block principles across 15 plus real case studies. If this resonated with you, the link is in the description.